So, somebody said it's got a nucleus. Yes, and that's left over from the planetary model. What else do you remember? Okay, Kane.
That there's orbitals where the atoms are most likely to be found.
Ooh, okay. Did you look at your notes?
No, I didn't.
Then you have an excellent memory. There are these things called orbitals where we're going to find electrons. Okay, what else do you remember? Cooper. Okay, it's one of the two models that we commonly use to talk about the atom, and we're going to talk a little bit about both the old planetary or Bohr model and the new quantum today. We're going to compare the two. Okay, what else? Okay, so you're connecting the idea of the orbitals and the electron cloud. We're going to just hold that part because I think you've got the connection a little bit skewed. So they're connected, yes. Okay, what else? What else do you remember? Beck. Okay, we can move electrons around. We can get them to jump. We can make them jump. Jump, electrons, jump. What else do you remember? Picturing the Yosemite Sam and Bugs Bunny cartoon. Do you know this one? You know this one. Yosemite Sam shooting at Bugs Bunny's feet and Bugs Bunny's jumping. Dance. Dance, Bunny, dance. I'm thinking of that with electrons. Okay, good. So you've got some ideas. Here's what we're going to be doing today. By the end of class today, what you are going to be able to do is identify specific locations for specific electrons with as much certainty as we can get and predict how many electrons you're going to find where. So this is pretty high-level stuff. We're going to do all this today. You're going to have a fifth quiz tomorrow. And then we're going to start actually placing electrons on Monday. Okay, so, oh, not this again. Okay, quantum model of the atom. And in the other class, somebody said, well, the quantum model comes out of a lot of people's work. It does. So it comes from the work of Planck, Einstein, de Broglie, Heisenberg, Schrodinger. And in the quantum model, so remember in the old Bohr model, we had neat little racetracks. We had little atoms or little electrons running around nucleus on little tiny racetracks, like little greyhound bunnies. You know what I mean? In the quantum model, we've got these big fuzzy areas where there's a real good chance you're going to find an electron. So it's like a BB wrapped in a giant wad of fluffy cotton candy. It's this big, fuzzy, amorphous thing. And that cotton candy is where you're going to find the electrons. That fuzzy space around a little tiny, dense nucleus. The picture up there is one that comes from the internet. It's an image of the quantum model. We very often call that fuzzy cotton candy the electron cloud. And we talk about the electron cloud collectively. We're going to talk about orbitals very specifically. We talk about the electron cloud collectively. As all the orbitals smash together, that's your cloud. Okay. So, Herr Schrodinger gives us these equations. Now, let's back up a second. Who is it who said, wait a minute, the electrons behave as both a particle, they're a particle for sure, but they behave as a wave. Who said that? Broglie, Louis, who wrote his doctoral thesis, and his advisor said, I'm not qualified to read this, send it to Einstein. Okay. So, Louis says they act as waves, Louis, Broglie. Schrodinger comes along and gives us equations for those waves. And those equations describe three-dimensional physical spaces. They're called orbitals. Now, carry over from the old Bohr idea. What was Bohr's big contribution? That there are what? Energy levels. Yeah, there are energy levels. So Bohr said there are different levels of energy. These orbitals are actually arranged in such a way they have different levels of energy. So that's sort of a carryover from the Bohr idea. Now, quantum numbers. Remember, this is the quantum model. Here's what I'm going to tell you about these quantum numbers. There's only one that I'm ever going to care that you know. The principal thing I want you to know is the principal quantum number. I don't care about angular momentum numbers. I don't care about magnetic numbers. Spin, you'll have to know a little bit about spin, but you don't need to know spin numbers. The principal quantum number is the same thing as the energy level. It corresponds to the energy level. So at the location where principal quantum number equals 1, guess what energy level you're on? 1. At the location where principal quantum number equals 2, guess what energy level you're on? 2. Oh, you guys are good. Yeah. Huh? This is very complicated, yes. We're going to see a lot of mathematical patterns today. Okay, so that's the only one that I really care that you understand. And principal quantum number is given as n. So we'll say n equals 1. That's first main energy level. So if I say n equals 4, what main energy level are we on? 4! Woohoo! Okay. This big chart should have showed up in your notes. Good, it did. So you'll notice on this that there are four columns, 4 rows, and on the side it says energy with an arrow pointing up. Because we're going to be talking about these things in order of increasing energy. Let's get rid of that. And I am going to move this back so far that you'll be able to kiss the screen if you want to. I need lots of markers for this. So, on main energy level 1, we call that, very creatively, 1. We talk about n equals 1, and have you heard the term shell in physical science? Okay, talk about the first shell, the second shell. Shell just means main energy level. That's all it means. So if we're on the second shell, we're on the second main energy level. I stress this because I think we get a little bit confused with shells and subshells and orbitals, and it gets confusing. So I want to make sure you got your terminology lined up. Okay. On that first main energy level, for each energy level we have subshells. On the first main energy level, the first orbital that we find, we only find one orbital. It's got a very simple shape. Got my toys right here. And that first main energy level has a little orbital that looks like that. That's an s orbital. So I'm going to draw it in here. And you can think of s as spherical. You can think of it however you want. But on the first main energy level, we have an s orbital. So I always call it a beach ball. This is my chemistry knowledge beach ball. It's got chem facts written all over it. You can whack people with it and whack chem facts right into their heads. It's great to take to the beach and play with. So, here's my question for you. I have an orbital shaped like this. How many ways are there to arrange it? Before you answer, imagine now that I have an orbital that is mysteriously shaped exactly like this marker. It's a weird orbital. If I arrange this marker this way, does it look different to you than if I arrange it this way? Or this way? Yeah. Well, that was this way, this way, this way. Looks different. What about this beach ball? So I've got this beach ball here. Aside from all the writing and the painting and the numbers and stuff on it. If I do that, does it look different? What if I do that? Look different? That? No, not yet? No. So for a spherical orbital, it does not matter how you arrange it, it looks the same. What this means is that we've only got one arrangement of a spherical orbital. Turns out we only get one orbital. So, this column, which is orientation, we can think of it as direction, how the orbital's arranged. We're going to draw the actual orbital in there. And we just get one. We get one spherical orbital on the first main energy level. Now, you have one sibling, right? Only one? Perfect. So if I send a card to your house that says Davis kid, that Davis kid, you know who to give it to? Assuming it's Summer and she's calling. Okay. We have no idea who gets the card. I have to be more specific. Well, here's the thing about those orbitals. Every orbital, no matter where it is, no matter what shape it is, no matter what energy level it's on, can hold 2 electrons. 2. Just 2. So, when I look at that s orbital, it can have 2 electrons in it. There has to be some way to differentiate them. And the way we differentiate them is spin. So rather than giving them a first name and putting it on the darn birthday card, we have up spin and down spin. Now here's a bit of a misconception. When we talk about something like spin in particle physics, and make no mistake, what we're doing here is a little bit of where particle physics meets chemistry and bumps up against it. This does not mean these things are spinning like little planets. It's a term we use. Honestly, truly understanding the nature of electron spin is way beyond my pay grade. I don't expect you to understand the true particle physics nature of electron spin. What I want you to know is we call it up and down. That's what I want you to know. For any orbital, we got 2 electrons in it. One is spinning up, one is spinning down. And if you want to think of them as running around like little hamsters in a wheel, that's your business. Okay, we go up to the second main energy level. What's the number there? 2. And here's the thing. No matter what energy level we go to, everybody gets an S. This is kind of like saying, I don't know, I got a point for putting my name on my paper. I'm not that special. Everybody got a point for putting their name on their paper. Everybody gets an s orbital. So on that second main energy level, we're going to have another s orbital. Now here's the thing. It's a little bit bigger. So you can see them on there. It's a little bit bigger. It's still a beach ball, though. Still not all that exciting. It's still spherical. So since it's spherical, how many ways are there to orient it? Just one. Which means, so we have our S, which means we only get one S, because there's only one way to orient it. Now, things are about to get more interesting. It's just to designate that that's an S. Because I need space, that's why. So things are about to get more interesting. We have p orbitals. And I call them the double drumsticks. That's p orbital. Double drumstick. Looks like 2 drumsticks fused together at the top like some sort of mutant chicken leg. We'll stick our double drumstick right there. Okay. Now, I'd like you to all stand up, please. And I want you to think about the Cartesian coordinate system. I know you were probably already thinking about the Cartesian coordinate system. My mind tends to drift too. It's okay. So, if you were going to talk about this orbital on the Cartesian coordinate system, what axis is it following? Why do you ask? Get it? Why do you ask? Why do you ask? Shh, thank you. Do you want to play symbols for me? I'd appreciate that. I can use it. So this is on the y-axis. Could we just as well orient it on the x? Yeah, we could. So we can do it on the x, and we can have it on the y. So I've got a little one here that's on the